Greetings of the day to all of you. Today I am going to deliver last lecture of this course on pulse width modulation techniques. Okay, the topic of discussion in today's lecture is a new type of pulse width modulation technique, which is also called DeltaSigma modulation technique. So we are going to discuss the last topic, that is delta sigma pulse width modulation, or you can call it in very simple words as delta sigma modulation. This is the topic of discussion in today's lecture. Before I discuss with you delta sigma modulation, I would like to recall what we discussed in the last lecture. In the last lecture, we discussed about hysteresis current control technique, or that is also called band-band control. Band-band control. That's another name given to hysteresis current control technique. If you remember what we did, we generated a reference current, sinusoidal reference current. Let's call that current as I star. Okay. We compared that sinusoidal reference current with actual load current I. And the error was error between the two currents. That was given to a hysteresis current controller. Okay, so this is the symbol of hysteresis current controller, something like this. Hysteresis current controller. Okay, then the hysteresis current controller at its output generated the gating pulses for the switches of PWM voltage source inverter. So I can show inverter with the help of a simple block like this. So with one IGBT with feedback diode, it does not mean our inverter comprises of only one switch. No, it is just the block diagram. If it is a two-level inverter, it will comprise of 6 such switches. Okay, so this is our PWM voltage source inverter, VSI. And the inverter generates the output voltage, and when that voltage is fed to the load, that results in the flow of current. This is the current I. And what we are doing, this is the current sensor. I write here current measurement block or current sensor. It senses this load current, and this load current is then compared with the reference current like this. Okay, if you remember, our reference current was something like this. We have already discussed it in details in last lecture. This was our reference current, purely sinusoidal in nature. Okay, and we created a band around this reference current, an upper hysteresis band like this in the positive half cycle, and a lower hysteresis band like this. And if this is our I star, we made our I to follow this I star within this hysteresis band. So this is the actual current I, which follows the reference current within this hysteresis band like this. Now, depending upon the hysteresis band, you can have a good quality of current. If hysteresis band is low, you can have very good quality of current, which is nearly sinusoidal in nature. So this is the actual current I. So therefore, if we take part of this current, for example, this is, let us take phase leg R of the inverter. If you take phase leg R of the inverter, phase leg R comprises of two switches, upper switch or top switch and bottom switch. Top switch is S1, bottom switch is S4, and the feedback diodes are D1 and D4 respectively. And then this is the DC bus. The DC bus capacitors drop a voltage of VDC by 2 respectively. And this is the total DC bus voltage VDC. Okay, and this is our phase leg R. Let us consider positive direction of this current I. Okay, you can call it IR, or in this case we call it I. Okay, let us take a portion of this cycle, just a portion of this cycle. It is something like this. Say I take the portion of the cycle, the foiling part of this half cycle, positive half cycle, in which the current is positive. Okay, so we have an upper, so this is our I star. So this is our upper hysteresis band. This is the upper hysteresis band, and this is the lower hysteresis band. Okay, this is the part of this waveform. See, this part of the waveform. And then the current fluctuates or oscillates between the two hysteresis bands, upper hysteresis band UHB and lower hysteresis band LHB. Okay, like this. So it will oscillate like this. I'm just showing, a few these ripples of the current. So this is your actual current, I. Okay. Now, from this instant to this, let me first of all draw these projections. Okay, fine. When current is rising, that means the top switch S1 is on. Gating pulse is issued to top switch S1 and current flows like this. So IR is positive and it is rising. And since your load has some resistance and some inductance, it's an RL type of load, maybe induction motor load, which has inductance also. So some energy gets stored in the inductive part of the load. And since load is connected to the source, it receives energy from the source, and the current starts rising. You can see current starts rising. So since our top switch S1 is on, the phase R is connected to positive DC bus and pole voltage VRO is plus VDC by 2. So if you draw the waveform for pole voltage VRO, so it is plus VDC by 2. Plus VDC by 2 during this period. As soon as the current reaches the upper hysteresis band, actually what happens, this comparator finds the error between the two. I mean, I star minus I. This is your I star and this is actual I. When current increases, it continuously finds the error between I star and I. So error is, let us call error as E is equal to I star minus I. I star is sinusoidally varying like this, and I is, for example, during this instant, I is rising like this. So you can see it will find the error, and therefore it will find the error, we call that delta I. So delta I is I star minus I. So this is your error, delta I. So what do? You create a hysteresis band, so say plus minus 0.01. So for example, this is plus 0.01 and this is minus 0.01. This is your hysteresis band. And what is this? This is delta I. That is the error between reference current and actual current. So at each instant of time, this comparator calculates this error. It subtracts from I star I. So it finds I star minus I continuously. And this is the error it generates. And as soon as this error touches the upper hysteresis band, 0.01, at that time you will see that your induction motor winding current has reached the highest value, positive peak. What it will do, it will change the switching status of the inverter phase leg. It will withdraw the gating pulse to S1 and it will issue gating pulse to bottom switch S4. But S4 cannot conduct, I have told you in the previous lecture also, because current is positive. So instead of S4 conducting, D4 will conduct. And therefore the inductance, load inductance, will start releasing the energy. And when load inductance releases the energy, then what will happen to the current? Current will start falling. So the current now starts falling. Okay, so aapka current error delta I, it also starts falling. And then it reaches the lower hysteresis band. For example, when your delta I reaches the lower hysteresis band, the switching status is again changed. Gating pulse to S4 is withdrawn and it is given to S1. So S1 gating pulse is again high. It again turns on and current again rises and then it again falls. This is what happens. So therefore during this period S1 is on and during this period D4 is on. D4. And when D4 is on, your phase R is connected to negative DC bus and pole voltage VRO is minus VDC by 2. Then it is again plus VDC by 2, minus VDC by 2, plus VDC by 2, minus VDC by 2. You can continue like this. So this is your pole voltage. Okay. This is what we have already learned in the previous class. Now, there is one very important characteristic of load. The load is inductive in nature. And inductive nature of load introduces integration effect. So I will write here. It's a very important point. Inductive nature of load introduces integration effect. Integration effect. Try to understand this point, because when a particular, say, this positive voltage pulse gets applied across the load, motor winding. What is voltage across the motor winding inductance? It is plus VDC by 2. Okay, and this voltage is given by L di by dt. So from this, the current which is flowing through the inductance or through the induction motor winding, that is given by 1 by L integral VL dt. So VL is plus VDC by 2. It integrates it, divides it by L, and you get I. And what you find? I increases during this interval. And then when bottom switch D4 conducts, current decreases, because negative voltage pulse minus VDC gets applied across the load, and when that is integrated, divided by L, you will find the current is now decreasing. It is decreasing, then increasing, decreasing. So this inductive nature of the load introduces this integration effect. And it is this integration effect which causes your current, load current, to oscillate between upper hysteresis band and lower hysteresis band like this, up and down like this. Okay, so this is very important. Now, we wish to, instead of controlling, see, this is current controlled PWM voltage source inverter. We have used hysteresis current control. And using hysteresis current control, we are basically controlling the load current. We are not controlling the load voltage. And by controlling the load current, we are making load current follow the reference sinusoidal current. And in that case, you will find that load voltage indirectly gets controlled. We are basically controlling load current. And we are making load current. We generate the 3 reference currents, say IR star, IY star like this, and IB star. These are our reference currents, and we are making actual load currents follow these currents. This is actual phase or current IR, this is IY, and this is IB. We are making them follow these reference currents within a very narrow hysteresis band. So therefore, using bang control or hysteresis current control, we are basically controlling the current, load current, induction motor winding current. And indirectly, we are controlling the voltage of the inverter also. Because if you check the voltage of the inverter, the pole voltage, the line voltages, or the phase voltages, you will find that their instantaneous average values are sinusoidally varying. So you are indirectly controlling the voltage. What you are directly controlling is current, load current. That's why these types of inverters are also called current controlled PWM voltage source inverters. By using the bang control or hysteresis current control, we are directly controlling the current. Now the question is, instead of controlling the current and by that way controlling the voltage indirectly, is it possible to control the voltage directly using similar type of hysteresis technique? Okay, let us try to see whether it can be done or not. So what I want, instead of controlling the load current, I want to control the load voltage. So I want my load voltage to be sinusoidal like this. So I want my load voltage V0 star to be sinusoidal like this. Say this may be a load voltage of a particular phase. Say phase R, then phase Y and phase B will also be similar but 120 degrees phase displaced. Let's take a particular phase. So I want my phase voltage or inverter output voltage to be sinusoidally varying like this. So what I do? I generate the load voltage, reference load voltage. In hysteresis current control technique or in bang control technique, we were generating the reference current, I star. Here we will not generate the reference load current, we will generate the reference load voltage. And we would like to control load voltage directly, not the current. We would like to control the voltage. But what type of voltage you have across the load? I mean, if you see the pole voltage is something like this. It is, say for example, If you see pole voltage V0, it is plus VDC by 2 minus VDC by 2. It oscillates between plus VDC by 2 minus VDC by 2. Okay, so you would have liked to create a hysteresis band around this reference voltage V0 star, and you would have wished to make your load voltage like this, follow this reference voltage within the hysteresis band, the same way you did in hysteresis current control. There, instead of controlling the load voltage, you are controlling the load current. This was your reference load current, this was the hysteresis band, and within this hysteresis band you are controlling the load current I. Is it possible to do that in case of voltage? The answer to this question is no, absolutely no, we cannot do that. The reason being, your reference load voltage V0 star is continuously varying, you can see, sinusoidally varying. But what about your load voltage? Load voltage is a discrete signal, it's not a continuous signal, it's a discrete signal. For some time it is plus VDC by 2, for some time it's minus VDC by 2. It oscillates between plus VDC by 2 and minus VDC by 2, or you can call this plus U minus U. It oscillates between plus U and minus U. At any instant of time, if you find the error between actual load voltage, I mean reference load voltage V0 star and actual load voltage, so that will be V0 star minus U. Say for example, if this is you take positive VDC by 2, it is plus U, I mean minus U. Okay, and then there may be switching, I mean instead of getting top switch getting gating pulse, bottom switch may get gating pulse, and your load voltage may jump from, it may transition from plus VDC by 2 to minus VDC by 2, that is plus U to minus U, and then your error will become V0 star plus U. I mean, we would like that our load voltage should follow, I mean it should follow the reference voltage within this hysteresis band. That's not possible because my reference voltage is continuously varying like this, and my actual load voltage, say pole voltage, it's not continuously varying, it's a discrete signal. You cannot compare a continuously varying signal and a discrete signal. You should have a signal like this, just like in hysteresis current control, and you could have compared that. I mean, you could have compared this signal with the reference signal, and then you could have made this signal oscillate between upper hysteresis band and lower hysteresis band around V0 star like this. That was possible if your load voltage was also varying continuously, not in a discrete manner. But we know that in case of PWM voltage source inverters, our load voltage is in the form of switched voltage pulses like this, plus VDC by 2, minus VDC by 2, or plus VDC by plus VDC 0, plus VDC 0, or minus VDC 0. It's a discrete signal, so it is not possible to create a hysteresis band and make this load voltage follow the reference load voltage like this. So that is the problem. In other words, you cannot subtract a continuously varying reference voltage signal V0 star from a discrete voltage like this. It's not possible. So does that mean that we cannot have direct control over voltage using hysteresis band? No, we can have, because we can do it because in order to obtain the similar behavior, similar to that of hysteresis current control, it is necessary to emulate the effect of integration effect of load. It's a very important statement, you note down. So I will write here, in order to obtain the behavior similar to that of hysteresis current control or bang control, it is necessary to emulate the integration effect of load. Integration effect of load. Just few moments back, you have seen in hysteresis current control, the load current is given by 1 by L integration V dt. At any instant of time, the voltage across load inductance is either plus VDC by 2 or minus VDC by 2. When it is plus VDC by 2, you integrate your current After integration, 1 by L integration VDC by 2 dt, it rises. And when your hysteresis current control applies minus VDC by 2 across the load inductance, then current through the load inductance is 1 by L integration minus VDC by 2 dt, and it integrates that, and so that is the integration effect. उस वजह से क्या होता था, if this was your reference current I star, your load current because of integration effect was oscillating between upper hysteresis band and lower hysteresis band within this narrow hysteresis band, and it was very closely following the reference current. That is not the case with direct voltage control. In direct voltage control, you have a reference voltage signal V0 star, and your actual voltage is not like this. It does not have integration effect like this, like you have in case of hysteresis current control, where current has the load has integration effect and current oscillates like this. Your voltage is discrete like this. It is plus VDC by 2 minus VDC by 2. Okay, so but what we can do, we can emulate the integration effect of load in case of hysteresis current control, and we can produce a similar behavior in this case in delta sigma modulation, if you want to control the voltage directly instead of controlling the current. How can we do this? Very important to note, this can be very simply obtained by using an integration circuit. Note down, this can be very simply obtained. I mean, this integration effect of load can be very simply obtained by using an integration circuit or integrating circuit. See, try to understand what we are doing, the instantaneous voltage error. See what we are doing. We find the instantaneous voltage error. Instantaneous voltage error. Delta, let us call that delta. Okay, and that instantaneous voltage error is reference voltage minus actual voltage. Now this actual plus or minus actual voltage. Actual voltage may be either plus U or minus U. So what we are doing, the instantaneous voltage error, which is this. See, this is your V0 star, and this is your V0. This is V0, actual V0. Okay, it has a positive value plus U and minus U, which is actually plus VDC by 2 minus VDC by 2. Let us call it plus U and minus U. When voltage is here, instantaneous error is delta. Instantaneous voltage error between this reference voltage and actual voltage is V0 star minus U. And when voltage across the load is minus U, then instantaneous voltage error is V0 star minus U, that is V0 star plus U. So what we are doing, this instantaneous voltage error is never zero. It can never be eliminated. Can never be eliminated. It's not zero, because in hysteresis current control, you have found that this current, the error between the reference current and actual current is very close to zero. Aapka hysteresis band very narrow hai. That means if this is your reference current, the actual current is very closely following this reference current within a narrow hysteresis band, and the error between the two currents is very, very nearly equal to zero. That is not the case if you want to, if instead of controlling the load current, you are controlling the load voltage, because your reference voltage is sinusoidal like this, but actual voltage is discrete like this. So this error can never be close to zero. Okay, so therefore it cannot be eliminated. But what can we do? But the accumulated error, we do not take the error, we take the accumulated error. Accumulated error, how do you get accumulated error? By integrating this error. So the accumulated error can be limited. It can be made very nearly equal to zero by ensuring that the integral, what we do, we integrate this error. Integral, and we call that integral summation, sigma. integral sigma of the error, voltage error, which is called delta, remains very close to zero. Very close to zero. See, try to understand. What we do, we find, just like जैसे कि हम hysteresis current control में करते हैं, I star और I में error हम निकालते हैं, and that error is maintained within this narrow hysteresis band, so that I is very closely following I star. But in this case, if instead of controlling the current, you are controlling voltage. The error between V naught star and V, this is your V naught star and V naught is, it can never be zero, because your V naught star is continuously sinusoidally varying, but your V naught is a discrete signal. Your V naught is not a signal like this, it is a discrete signal like this, plus U, minus U, plus U, minus U, like this. What you do, again, just like in hysteresis current control, you take the error between the two. So for example, at this instant of time, you take the error between the two voltages, V naught star minus V. Okay, so it will be V naught star minus U, and for this it will be V naught star plus U, then V naught star minus U, V naught star plus U, and so on. And what we do, this error, we integrate this error. In hysteresis current control, load inductance was having integration effect automatically, because load current was 1 by L integration V dt. It was naturally having integration effect, and that was making load current continuous like this. But in case of in this case, in case of voltage does not, load voltage does not have any integration effect. But what we do, we find the error between reference voltage and actual voltage, and we integrate this error. Okay, and the integration means taking sigma of this summation, and hence taking the accumulated error. And when we integrate this error, your error, integrated error, also becomes like your current, load current, जो आपने अभी last lecture में देखा, in hysteresis current control, load inductance has integration effect, which makes your load current like this. So in this case, what we are doing, the error is not, the error between V naught star and V naught is not like this. But if this error between the two voltages, between reference voltage and actual voltage, if the error is integrated, so if delta is integrated, you are taking sigma of delta, okay, then your integrated error, जो आपका integrated error आएगा delta sigma, okay, जो आपका error है delta, आप उसी का integration लेते हो, वो, that becomes something like this. और आप उसी को, and that sigma of delta within, that is maintained within a narrow hysteresis band, and hence a direct control over the voltage is obtained. Okay, so this gives rise to, I will write here, this gives rise to the term delta sigma, and hence delta sigma modulation, This is where from this has got the name. This PWM technique has got name from here. What you are doing? You are taking the error between reference voltage and actual voltage, and you are integrating that error. Error is delta, integration is sigma. So that's why it's called delta sigma modulation. Delta is the error and sigma is the integration of that error. And when the error is integrated, that error becomes like this. जैसे कि hysteresis current controller में आपकी current में integration effect था और वो ऐसे oscillate होती थी. इसी तरह इसमें delta sigma modulation में your voltage is not oscillating like this, but the error between the two voltages, you are, after integrating that, you are making that oscillate like this between upper hysteresis band and lower hysteresis band. Okay, hence the name delta sigma modulation. So delta sigma modulation means you are comparing the sinusoidal reference voltage with the actual load voltage, and the error delta is then integrated, and that integration is represented by the symbol sigma, and then that integration effect makes the integrated error like this, and you maintain this integrated error within the hysteresis band, just like you do to the current in hysteresis current control technique. Since the error between the reference voltage and actual voltage, that is delta, is integrated. Integration is sigma. Hence, this pulse width modulation technique is also called delta sigma modulation. Okay, delta sigma pulse width modulation, delta sigma modulation. It will be very much clear to you if I try to explain it with the help of a waveform. But before that waveform, I would like to say that the sigma, that is the integration, is given by 1 by tau integral 0 to t delta dt. What is delta? What is delta? Delta is V naught star minus V naught. Okay. V naught star is your sinusoidal reference voltage and V naught is actual voltage. वो error delta आप उसी का integration लेते हैं, that is sigma, hence the name delta sigma modulation. So therefore integration sigma means integration is equal to 1 by tau integral 0 to t. What is delta? Delta is V naught star minus V naught dt. Okay, and its value means value of sigma. Sigma, what is sigma now? Sigma is nothing but it is the integration of the error between reference voltage and actual voltage. Okay, so its value means the value of the sigma integration. The value of sigma is kept between two threshold values. Let us call those threshold values plus s and minus s, using a comparator with hysteresis, just like in hysteresis current control, using a comparator with hysteresis. You are first of all taking error between actual reference voltage and reference voltage and actual voltage. You are then integrating that error, so delta sigma. Okay, and that integrated error sigma is then kept between two threshold values, upper hysteresis band and lower hysteresis band, using a comparator with hysteresis. Okay, it will be clear to you if I draw a simple waveform to explain it. See, this is how I will try to explain it. This is my load voltage V naught T, output load voltage, and I want to directly control, instead of controlling the current as we were doing in hysteresis current control, in delta sigma modulation we would like to control the voltage directly. Okay, and my voltage is, say for example, my voltage is like this. My load voltage, which can be, say, a pole voltage, it's something like this. Let me take a couple of cycles like this. It is plus VDC by 2, minus VDC by 2. Agar aap inverter, if you draw the inverter phase leg, say phase leg R, like this. So this is S1, S4, D1, D4, and let us say output voltage is V naught, output voltage. I am not talking in terms of current, I am talking in terms of voltage, because in delta sigma modulation we are directly controlling the voltage. We are not controlling the load current, we are directly controlling the load voltage. So my during this period the bottom switch D4 is on. Okay, D4 is on. Say if the current is positive, then the bottom switch D4 is on, and pole voltage VRO or V naught is minus VDC by 2. It's minus VDC by 2. So instead of writing it minus VDC by 2, let me call it minus U. So U is basically VDC by 2. And when top switch, during this period, top switch is on, that is S1 is on. And if current is positive, then V naught is plus VDC by 2. So this is plus VDC by 2, plus VDC by 2 means plus U. So therefore my load voltage oscillates between minus U and plus U. That's minus VDC by 2 plus VDC by 2, and it continues like that. Okay. But my actual voltage, I would like to have my actual voltage like this. I mean reference voltage. This is my reference voltage. V naught T star. My reference voltage is basically sinusoidal. अगर मैं एक साइकिल लूँगा, एक साइकिल से switching frequency of 10 or 20 kilohertz, एक साइकिल मुझे almost constant दिखेगा. So this is my reference voltage, V naught star. This is V naught star T. I am taking just one cycle of this, so it is constant. So I would like to have my load voltage not oscillating like this. I would like to have it like this. Okay, I would like to have my load voltage follow this reference voltage V naught star. This is star. This is the reference load voltage. Okay, so what I will do, I will find the error between the reference load voltage V naught star and actual load voltage, which is discrete like this, and that error will give me delta. So what is delta? Delta is reference load voltage V naught star minus actual load voltage, and actual load voltage या तो plus U होगी या minus U होगी, because it is either minus U plus U. And then I integrate that. I integrate this error using the integration circuit. Just few moments back I have written this integration is 1 by tau integral 0 to t V naught star plus minus U dt. Integrate. And when I integrate this, I get the integrated signal like this. So I will show you. And I make that integrated signal to oscillate between upper hysteresis band and lower hysteresis band. So मैं दो threshold value पहले ही decide करता हूँ, say S minus S. It may be plus 0.01, it may be minus 0.01, or plus 0.02, minus 0.02. ये hysteresis band पहले आप decide करते हैं, depending upon the switching frequency. और ये sigma जो है, sigma is basically integration of the error delta. It is integration of error delta. So we try to keep it within this hysteresis band, within these two threshold values using a hysteresis circuit. Okay, so therefore I first of all set upper hysteresis band, say S. This is S, upper threshold, and lower threshold. Lower threshold is minus S. So just let us see what happens during this instant of time. Here at t equal to 0, what is your inverter output voltage? Output voltage is equal to minus U. You can see at t equal to 0, t equal to 0. What is inverter output voltage? It is minus U, minus VDC by 2, or we have written that minus U, right? So therefore, what is error? Error between reference voltage and inverter actual output voltage, delta. What is your reference voltage? Reference voltage is V naught star minus the actual voltage. And what is actual voltage? You have seen the actual output voltage is minus U. So minus into minus becomes plus. So this becomes V naught star plus U. तो ये आपका delta बन जाता है. And what will integrated circuit do? Integrated circuit इसको integrate करेगा इस error को. It will integrate this error. So it will integrate this. That means 1 by tau integration of delta. Delta क्या है? It is V naught star plus U dt, 0 to t. So it will integrate this. And when it integrates this error, so U is here VDC by 2 plus VDC by 2. Error को जब integrate करेगा, so error will start rising. After integration, the error will start rising. ये rise होना शुरू हो जाएगा. In a similar way, जैसे आपके hysteresis current controller में current was given by 1 by L integration V naught dt. जब आपकी load voltage plus VDC by 2 थी या plus U, ये उसको integrate करता था divide by L, so वो current rise होती थी. In a similar way, यहाँ पे ये क्या करता है? यहाँ error, first of all, at t equal to 0, it finds error which is V naught star plus U, and then it integrates that error. Just like when current is integrated, it rises. And similarly, when this voltage, error voltage is integrated, so V naught star plus VDC by 2, it's plus VDC by 2 here. So, integration के बाद ये error ऐसे current की तरह rise हो जाएगा. So, this error will rise. अब देखिए, it's very interesting to see. So what is this now? This is now sigma. Yeah, sigma, it is the integration of the error. It's not basically error, it's the integration of the error, or a integration of error sigma, which we also call as sigma, it rises. And as soon as it touches the upper hysteresis band, आपने पहले ये threshold set किया है, so your control logic circuit will issue gating pulse to top switch S1. इससे पहले इसने bottom switch को ये दिया था gating pulse, और bottom switch में अगर current आप positive लेते हैं तो D4 was conducting. So then it will, when your integration of error sigma touch the upper threshold value or upper hysteresis band, the logic, gating logic will change. So the gating pulse of S4, which was higher earlier, it will become now low, and the gating pulse of S1, which was low, it will become high. That means S1 will now turn on, and when S1 turns on, current flows like this. I'm not actually interested in current, I want to see what is the voltage now. And since top switch S1 is on, so this phase is connected to positive DC bus, and this pole voltage is plus VDC by 2. Plus VDC by 2 means plus U. So therefore earlier your voltage was minus VDC by 2. It jumps from minus VDC by 2 to plus VDC by 2, or it jumps from minus U to plus U, क्योंकि अब आपका top switch S1 on हो जाता है. Okay. अब जब आपका when top switch turns on, again it is very interesting. So now when top switch turns on, what is your error? Error is now again reference voltage minus actual voltage. What is your actual voltage? It is plus U. So it is, what will this error will go to integrated circuit. Integrated circuit क्या करेगा? That will find sigma. Sigma equal to 1 by tau integration 0 to t delta dt. Delta आपका है V0 star minus U dt. Now what is your U? U is minus, it is minus U. Minus U means minus VDC by 2. और चूंकि ये negative को, now since this is a negative quantity, इसका when you integrate this, so this sigma will decrease now. It is just like this in hysteresis current control when minus VDC by 2 was applied across the load, across the inductance. So I was becoming 1 by L integration minus VDC by 2 dt. And since this was minus VDC by 2, current was decreasing. In a similar way, what will happen in delta sigma modulation? The error, after when it is integrated, when the error is integrated, okay? The integrate, this U, it is it is V0 square minus U, it is minus VDC by 2 here. And when it is integrated, integration will decrease this sigma now, क्योंकि ये minus अब हो गया है, voltage minus हो गई है यहाँ. And therefore, what will happen to this sigma? Sigma will now decrease. It will decrease linearly till it touches the lower threshold. And during this entire period, top switch is on. And as soon as it touches the lower this threshold or lower hysteresis band, control circuit यहाँ फिर से logic change करेगा. S1 की कंट्रोल पल्स हाई थी, अब वो लो हो जाएगी. S4 की लो थी, वो हाई हो जाएगी. सिंस S1 टर्न्स ऑफ नाउ, S1 जो ही टर्न ऑफ हो जाता है, D4 फिर से टर्न ऑन हो जाता है, और आपकी पोल वोल्टेज फिर से माइनस VDC by 2 हो जाती है. माइनस V, ये फिर से माइनस V हो जाती है, और D4 अगेन कंडक्ट्स माइनस U हो जाती है. एंड इट कंटिन्यूज, इट विल कंटिन्यू लाइक दैट. सो देयरफॉर आपकी, you are now controlling the inverter output voltage, pole voltage. Okay, you are controlling it by maintaining the sigma. What is sigma? Sigma is integration of the error within a narrow hysteresis band plus minus S. This is how you achieve it. Okay, so therefore, अगर मैं if I try to explain it with the help of a block diagram, which is very interesting block diagram. So my block diagram is something like this. In closed loop, I may generate the reference load voltage, V0 star, which is purely sinusoidal. This is my V0 star. I want to control my load voltage in this manner. Okay, my reference load voltage is V0 star, which is sinusoidally varying, and I want my actual load voltage, V0, to follow this reference load voltage very closely. Now, what will this comparator do? With the help of voltage sensor, it will sense the load voltage, which may be either plus U or minus U, and it will compare that load voltage with V0 star, reference load voltage, and यहाँ से क्या होगा? यहाँ से error produce होगा. And what is that error equal to? that error is equal to V naught star minus U or V naught star plus U, depending upon whether plus VDC by 2 is applied across the load or minus VDC by 2 is applied across the load. And then what happens to that error? That error is given to an integrated circuit. यह आपका integrated circuit है. So you can use an op-amp operational amplifier, and you can design using an operational amplifier you can design an integrated circuit. If you are trying to implement it through hardware, or if you are trying to implement it through software, say Simulink, and Simulink integrated circuits are readily available in the Simulink library. Or you can write a program and you can integrate this error. So what will this integrated circuit do? It will integrate this error. And when it integrates this error, it gives rise to sigma. So delta gets converted into sigma. Delta is error and sigma is integration of this error. That's why this technique is called DeltaSigma modulation. And now, what is this sigma? Yes, sigma is it is between plus S and minus S. We want it to remain between plus and minus S. How will we do that? We will give it to a hysteresis circuit or hysteresis controller, which is like this. This is our hysteresis circuit. जहाँ पे already we have upper hysteresis band, lower hysteresis band. We have already defined that. And when the sigma, this is our sigma. When the sigma is given to this, the sigma will oscillate between upper threshold plus S and lower threshold minus S. How? By the generation of gating, appropriate gating pulses, which are given to the switches of the PWM voltage source inverter. PWM voltage source inverter I will show by simple block like this. ये मेरा PWM voltage source inverter है. And then this is the load. It's a three-phase inverter basically, but I am showing it on single line diagram. This is the load. I may have a voltage sensor here which will sense the load voltage V0, and that V0 is directly fed to the comparator. So V0, it may be either plus U at any instant of time or minus U. Plus U means plus VDC by 2 and minus U means minus VDC by 2. This is the load voltage. I mean, if you consider pole voltage, your pole voltage is either plus VDC by 2 minus VDC by 2. If you are sensing the pole voltage, if you are sensing the line voltage, it may be plus VDC and 0. Anyway, so this voltage is then compared with the sinusoidal reference voltage. Error is produced. That error is integrated in the integration circuit, and then we get sigma. Sigma means integration of the error. So delta is converted into sigma, and then that sigma is given to the this hysteresis controller, and hysteresis controller makes that sigma to oscillate between plus S and minus S, upper threshold and lower threshold. That's within the narrow hysteresis band, and it appropriately issues gating pulses to the switches of the inverter, so that your load voltage, emulates, or your load voltage follows very closely the reference voltage. So it is, I can draw it like this. Waveform will be something like this. This is your V0 star. I mean, I want my reference voltage to be sinusoidal like this. So this is 0, pi, 2 pi. Let me take one phase voltage. In case of a three-phase inverter, I will have two similar reference voltages. So this may be VR star, VY star, and VB star. So let me take for one phase. Okay, and then inverter will have, in what your controller DeltaSigma modulator will do, it will sense the load voltage. It will compare that load voltage with reference load voltage at all instants, and the error delta will be integrated. Okay, and the integration of the error will give nothing but sigma, and that sigma may varies like this. देखिए वो sigma इस तरह vary कर सकता है within plus S and minus S like this. Let me show you in a better way. So it may vary like this. So this is plus S and this is minus S. So this sigma, which is the integration of the error, it is maintained between plus and minus S by hysteresis controller, which I have shown in the block diagram just few moments back by either issuing gating pulse to top switch or bottom switch. Okay, so then your load voltage. So let us, in the load voltage we would like to take the pole voltage V naught like this. Let me draw these projections first, then it will be very much clear to you. Fine. We already know, just few moments back we have seen when your inverter output pole voltage is minus VDC by 2. Okay, when it is minus VDC by 2, the error is this is the error. So delta is V naught star plus U, and when this is integrated, sigma is 1 by tau integration 0 to t V naught star plus U dt. So what happens to the sigma? This is your sigma. Then this sigma after integration it increases. As soon as it reaches upper threshold value or upper hysteresis band, the bottom switch is turned off and top switch is turned on. So यहाँ से यहाँ तक bottom switch आपका on था. And when bottom switch was on, your pole voltage was, say for example, minus VDC by 2. और उसके बाद top switch on हो जाता है. I have explained it with the help of another diagram waveform just few moments back. और उसके बाद top switch on हो जाता है. And when top switch turns on, your pole voltage becomes plus VDC by 2. It transitions from minus VDC by 2 to, this is plus VDC by 2. Okay? और जब ये प्लस VDC by 2 हो जाती है, आपका एरर क्या बन जाता है? Your error now becomes V naught star minus U. और जब उसकी integrated circuit will integrate that error. So that is in 1 by tau integration 0 to t V naught star minus U dt. Since it is minus U now, minus VDC by 2, वो error अब decrease होना शुरू हो जाएगा. You can see that error falls. And as soon as it touches the lower hysteresis band or lower threshold, so your control logic circuit will now withdraw gating pulse from S1. It will give gating pulse to bottom switch S4. Bottom switch में diode on हो जाएगा और आपकी pole voltage फिर से minus VDC by 2 हो जाती है, and it continues. This is how it works. Plus VDC by 2, minus VDC by 2, plus VDC by 2, minus VDC by 2. ये पॉजिटिव हाफ साइकिल कंप्लीट हो गया. उसके बाद नेगेटिव हाफ साइकिल में ऐसे होता है. This is how your load voltage vary. You can very interestingly see, अगर आप instantaneous average value लोगे इस pole voltage का, the average value of this is small. Then as you move towards the peak, you can see the widths of pulses increase. और corners की तरफ जब आप जाते हैं, the widths of pulses decrease. So instantaneous average pole voltage will be sinusoidally varying like this. Similarly, negative half cycle में इस voltage pulse की width कम है, इसकी ज़्यादा होगी, इसकी और ज़्यादा, फिर कम. So it will instantaneous average pole voltage sinusoidally vary. So therefore, your inverter output voltage is still in the form of discrete pulses, voltage pulses. But in its instantaneous average value very closely follows the reference value. Since your reference load voltage is sinusoidal, the instantaneous average pole voltage and hence instantaneous average line voltage and instantaneous average phase voltage will also be sinusoidal like this and in phase with this voltage. So therefore, we are directly controlling the inverter output voltage through the integration of the delta. So by delta sigma modulation. Okay. So this is how we do it. Okay. So I hope this is clear to you. So that's why it's called delta sigma modulation. Now, switching frequency is given by, or we can write V naught star minus U into T plus by T is equal to minus 2S, and V naught star plus U into T minus by T is equal to, it's not T, actually it is time constant tau is equal to plus 2S. अभी थोड़ी देर पहले मैंने आपको एक वेव फॉर्म दिखाई थी. I may have to reproduce that wave form when I was explaining delta sigma modulation. This was your inverter output voltage, pole voltage, of course. Okay, so this was V naught T, and this was my reference load voltage, V naught star T, and this was upper threshold value or hysteresis band plus S. This was lower threshold value or lower hysteresis band minus S, and this was sigma. Sigma was varying like this. Sigma was varying like this between upper and lower hysteresis bands like this. What was this? This was sigma. Okay, so this is plus U and this is minus U. And this instant during which your load voltage is plus VDC by 2 or plus U, it's T, called T plus. And this instant of time during which load voltage is minus VDC by 2 or minus U, it is called T minus. And total time interval is T. Okay. So during this period, what is error between error? Error is reference voltage minus actual voltage. What is my actual voltage? Is U. So that's what I have written here. V naught square minus U. And this error we are taking during time interval T plus. T plus by tau is equal to minus 2S. Why minus 2S? Because ये plus S है, ये minus S है. If you go from minus S to plus S, it is minus 2S. Minus S, that's minus 2S. अच्छा, उसके बाद आप ये instant ले लीजिए. During this instant, what is delta? Error. Error is again reference voltage, V naught square, minus actual voltage. What is actual voltage? Actual voltage is minus U. Minus into minus is plus. So that's what I am writing here. And this is during the time interval T minus. So V naught square plus U T minus by tau is equal to 2T is equal to 2S. 2S क्योंकि आप plus S से minus S की तरफ अब जाते हो. When you are going from plus S to minus S, so this is S minus minus S, so S plus S is 2S. Okay. So these are two equations. So therefore, from these two equations, switching frequency is given by following equation. If you want to find switching frequency, that is given by Fs equal to 1 by T plus T minus. Yeah, 1 by this total time interval is the switching frequency. And if you find it mathematically it will be U by 4 tau S. यहाँ से आप you find T plus and you find T minus. From this equation you can find T plus. It will have some value, and from this equation you find T minus. Substitute here 1 by T plus T minus. So that will, when you substitute that here, I leave that to you. You please do that. It will be U by 4 tau S into 1 minus V naught star square by U square. This is what you get. So this will be switching frequency. And let me tell you that in delta sigma modulation, the switching frequency is not constant. Whereas in sine triangle PWM, which you have studied earlier in module number 2 or module number 3, the switching frequency is constant. But here it's not constant. Switching frequency is variable. Just like in hysteresis current control, switching frequency is variable. Here also, switching frequency is variable. It is not constant. Okay. So that's all about delta sigma modulation. So I hope this is clear to you. And the question is, why should we go for delta sigma modulation? We have already studied some other modulation techniques or PWM techniques like sine triangle PWM, or which is also called naturally sampled PWM. What is the difference between delta sigma modulation and sine triangle modulation. Sine triangle modulation also gives us pole voltage like this. Say positive half cycle and then negative half cycle like this. And delta sigma modulation also gives us pole voltages like this, which are sinusoidally, whose instantaneous average values vary sinusoidally. What is the difference between the two, and which one is more beneficial or more advantageous? If you want to find the advantage or you want to compare the two techniques, harmonic spectrum for delta sigma modulation is broader. Harmonic spectrum for delta sigma modulation, delta sigma PWM or delta sigma modulation is broader. Broader means it will have large number of side bands. इसमें side bands बहुत होते हैं which overlap. So therefore, as far as if you calculate the THD in delta sigma modulation will be more or less same. THD of the voltage or THD of the current, it will be more or less same as in case of sine triangle PWM, with a small, it may be slightly less in delta sigma modulation as compared to sine triangle modulation, but the difference is not much. However, this delta sigma modulation, you can see as far as implementation is concerned, it is easier to implement. You have to simply create a band. You have to find the error. That error is to be integrated by integration circuit and then given to the hysteresis controller, and hysteresis controller tries to keep that sigma, the integration of that error, that sigma within the narrow hysteresis band, and it generates very easily the gating pulses for the switches of the inverter. Okay. Generally, it has been seen that delta sigma modulation is not very popular in PWM voltage source inverters, because this sine triangle PWM is much easier to implement. If sine triangle PWM is already a tested method, PWM technique, and it has already been used for decades, and it is very simple to implement, why should we go for delta sigma modulation? Because one problem with delta sigma modulation is the variable switching frequency, which may be a concern. So why should we go for delta sigma modulation? So that's why in PWM voltage source inverters, delta sigma modulation is not very popular. However, delta sigma modulation is very popular in matrix converters, which I hope Dr. Tabish may deliver a couple of lectures, 1 or 2 lectures on matrix converters to you in modern power electronics course. It is popular there because in matrix converters, we cannot use sine triangle modulation. So I will write here delta sigma modulation technique or delta sigma PWM technique or simply delta sigma modulation technique is not very popular in PWM voltage source inverters, but it is a very popular PWM technique for matrix converters. We have already published some IEEE transactions, myself and Dr. Tabish along with Professor Bhim Singh of IIT Delhi. We have used this delta sigma modulation for matrix 3-phase to 3-phase matrix converters, and we got some very good results in our power electronics laboratory, some very good hardware results. That was done by Dr. Tabish during her PhD research work under the joint supervision of Professor Bhim Singh of IIT Delhi and myself at NIT Srinagar, and we published IEEE transactions, one publication on delta sigma modulation applied to matrix converters. We had one IEEE transaction, one publication in IEEE transaction on power electronics, okay, which has a very high impact factor. So therefore, this delta sigma modulation is very popular in matrix converters rather than in PWM voltage source inverters. With this, I will end my today's lecture, and I am very pleased to inform you, I declare the end of syllabus of your a beautiful course on pulse width modulation techniques. Let us summarize what we have done, what we have learned over last 3 to 4 months. So right from the month of March, April, and now May. It's almost 3 months or almost over. In these 3 months, I have been discussing with you various lectures, various topics in this course on pulse width modulation techniques. Earlier, we conducted classes in electrical engineering department of the institute. We conducted the classes, offline classes. Around about 15 to 16 offline classes were conducted there. And later on, because of worsening COVID situation, we were forced to go for online mode of teaching. And I chose to pre-record my lectures at my home and some lectures in my office and send you the recorded lectures. Because it was your demand also to pre-record the lecture rather than having online classes. And I really enjoyed recording these lectures, discussing with you PWM techniques, various types of PWM techniques in quite details, and sending you the links of these video lectures. So our syllabus on pulse width modulation techniques, this course was divided into 4 modules. In module 1, if you remember, we discussed mostly about switches, single quadrant switches, 2 quadrant switches, and 4 quadrant switches. And we have seen how we can electronically realize a single quadrant switch, a 2 quadrant switch with unidirectional current and bipolar voltage blocking capability, and a 2 quadrant switch with unipolar voltage blocking capability but bidirectional current carrying capability. And then 4 quadrant switches were also electronically realized by us in that module, which has a bidirectional current carrying capability, a switch which has bidirectional current carrying capability, and bipolar voltage blocking capability. Then we started studying the basic structures of 2-level voltage source inverter and multi-level voltage source inverters. I first discussed with you realization of 2-level voltage source inverter using single pole double throw switch, and then we tried to electronically implement the single pole double throw switch using 2 quadrant IGBT switches, IGBTs with anti-parallel connected feedback diodes, and I have shown you how we can electronically realize a 2-level voltage source inverter. Then we discussed multi-level inverters, like first 3-level inverter, then 5-level inverter, and diode clamped voltage source inverter. And I told you how we can, for example, a 3-level inverter can be implemented by using single pole triple throw switches, and 5-level inverter can be realized by using single pole 5-throw switches. 7-level diode clamped inverter can be realized by using single pole 7-throw switches. And then I have also discussed with you complete electronic realization of 3-level diode clamped voltage source inverter and 5-level diode clamped voltage source inverter. That was about module number 1. And in that module, we also discussed about other types of multi-level inverters, like flying capacitor multi-level inverters and cascaded H-bridge multi-level inverters. It was discussed with you the structures of 3-phase 2-level voltage source inverters and 3-phase multi-level voltage source inverters. It was discussed in great details with you. Okay, that was about module 1. Then we started discussing module 2 in the offline classes. And in the module 2, first of all, I told you what is the aims and objectives of pulse width modulation. Objectives of pulse width modulation. I told you that main aim and main objective of pulse width modulation is to have a control over inverter output voltage, and also control over voltage, control over frequency of output voltage of the inverter, and simultaneously suppression of the harmonics, mitigation of the effects of the harmonics. That's main aims and objectives of pulse width modulation. Okay, and then we discussed, if you remember, the low switching frequency PWM, low frequency PWM. If you remember, we discussed selective harmonic elimination PWM techniques, offline optimized PWM techniques, stored waveform PWM techniques. We have seen that how we can calculate switching angles. If you use two switching angles, you will be able to eliminate one particular harmonic, say fifth harmonic. If you select two switching angles, you will be able to eliminate two harmonics, and so on. If you choose three switching angles, you'll be able to eliminate two harmonics, say fifth and seventh. We have discussed this low frequency PWM, selective harmonic elimination PWM technique in quite details using switching angle plane. We have tried to eliminate fifth harmonic component of inverter output voltage, seventh harmonic component, and both components, and combination of those. And we have discussed offline optimized PWM techniques, stored waveform PWM techniques using low frequency PWM. That was about module 2. And then in module 3, if you remember, I discussed with you the various types of high frequency PWM techniques. We discussed high frequency PWM techniques. In high frequency PWM techniques, we discussed we divided them into continuous PWM techniques and discontinuous PWM techniques. As far as continuous PWM techniques are concerned, the first PWM technique we discussed was sine triangle or sinusoidal PWM technique. First, we discussed it with regard to single phase PWM voltage source inverters, where we first discussed bipolar PWM technique, then unipolar PWM technique, then we studied the advantages of unipolar PWM technique over bipolar PWM technique. And then in single phase PWM voltage source inverter, I discussed with you the injection of common mode signal, how we can inject common mode signal for bus clamping. Okay, we discussed two types of bus clamping in single phase voltage source inverters. First, bus clamping with unequal loading of the devices, and then bus clamping with equal loading of the devices. That was about single phase PWM voltage source inverters. And then we discussed three phase PWM voltage source inverters. In three phase PWM voltage source inverters also, we started with naturally sampled PWM or sinusoidal PWM, or what we call a sine triangle PWM. Okay, we discussed it in great details. We discussed the harmonic spectrum and all that. And then I discussed with you the injection of third harmonic component with the sinusoidal modulating waves, adding those to sinusoidal modulating waves and giving rise to third harmonic injection PWM technique. Okay, that was also a form of continuous PWM technique. And then we discussed various discontinuous PWM techniques, where we injected common mode signals, which were mostly triple frequency. These common mode signals, we added them to original sinusoidal modulating waves, and we got various types of discontinuous PWM techniques, which we also called as bus clamping PWM techniques. Among the bus clamping PWM techniques, the PWM techniques which we studied in our discussions were 60-degree clamp PWM technique, 30-degree clamp PWM technique, bus clamping technique, and then continual clamp PWM technique, split clamp PWM techniques. Okay, we discussed those with the help of waveforms in quite details, their advantages, their drawbacks. Okay, and then we studied space vector. Our next module, that's module number 4, was mostly dedicated to space vector PWM technique, which was a new concept. Okay, I discussed with you the basic concept of space vector. What is a space vector? How to generate space rotating reference vector or space vector? What is the basic concept of space vector PWM technique? How to generate the rotating reference vector, and conventional space vector PWM technique. I discussed in great details with you using space vector diagram. And then I discussed with you space vector based bus clamping techniques. Conventional space vector PWM technique is also a continuous PWM technique, whereas space vector based bus clamping techniques, space vector based bus clamping techniques and space vector based advanced bus clamping techniques, which we studied in details, those are discontinuous PWM techniques. So we studied space vector based bus clamping and advanced bus clamping PWM techniques. Advanced bus clamping PWM techniques. And I told you that this conventional space vector PWM can be implemented through triangle comparison also by injecting a common mode signal M mid, MCM, which is equal to 0.5 M mid. Okay, and we will get same results as conventional space vector PWM. So we then discussed space vector based bus clamping and advanced bus clamping techniques. We studied the concept of stator flux ripple, how to reduce the stator flux ripple using conventional space vector PWM technique or space vector based bus clamping techniques and advanced bus clamping techniques, the torque ripple in induction motors and hybrid PWM techniques which we can use for reduction of torque ripple in induction motor drives. We discussed that in details. Then I discussed with you the effect of inverter blanking time or inverter dead time on inverter output voltage, effect of dead time on inverter output voltage in a couple of lectures. Then I also discussed with you overmodulation. First we discussed overmodulation from sine triangle PWM perspective, then from space vector PWM perspective. And we have seen how we can implement this overmodulation techniques in sine triangle PWM methods and in space vector PWM methods. And that overmodulation was covered in about 3 lectures. And then I discussed with you, PWM techniques applied to multi-level converters. And in last lecture, I discussed with you bank control or hysteresis current control in current controlled PWM voltage source inverters. And today's lecture, which was the concluding lecture of our syllabus, I discussed with you a new technique of PWM pulse width modulation, that is DeltaSigma pulse width modulation or DeltaSigma modulation. And I told you that this DeltaSigma modulation is not very popular for PWM voltage source inverters, but it is very popular in matrix converters. So that is all about various types of PWM techniques. Let me tell you, my dear students, that these PWM techniques, please study these PWM techniques in great depths. Try to learn them. They are really very interesting. I have tried to make this subject very informative and very interesting. If you study them and you try to, after your exams are over, you will get a gap of 1 to 2 months. Try to design the simulation models, implement these PWM techniques using software, say MATLAB, Simulink software you may use, or any other software you are well versed with. You will really enjoy this subject. And let me tell you that pulse width modulation techniques, PWM techniques, are heart of any power electronic converter system. Whether you use your power electronic converter system for custom power devices, for power quality improvement, or in facts, in HVDC systems, or in electric drives, or in any other application, switch mode power supplies, or any other application, these pulse width modulation techniques play a very important role in determining the proper working of the inverter or converter, and how efficiently your converter will work, and how properly it will generate the results. It will fulfill the control objectives. A pivotal role, a vital role is played by how accurately you apply the modulation algorithm or pulse width modulation technique for the operation of that converter. So these PWM techniques are heart of your power electronic systems. Please learn this subject by heart. Learn this subject, devote most of the time to learning this subject. If you have learned this subject, let me tell you, you can do a quality research work in your MTech projects and dissertation work. And some of you may later on go for PhD work, PhD research. With a strong background of pulse width modulation techniques, you will really produce a quality research. You will really do a quality research. Okay. Total number of lectures which I have spent in this in this course, I have completed 100%. I declare 100% course coverage. I have not left even a single topic untouched. So almost 100% syllabus I have covered. Okay, and let me tell you, it would not have been possible without your active participation, without your cooperation. I thank you all for cooperating with me, for being very patient, listening to my lectures, watching my lectures, and giving your feedback. And I feel very pleased. I'm really, pleased to tell all of you that I did not keep these video lectures private. I made them public so that students from all over the country, all over India, they get wherever there are PG or UG students or PhD students who are studying these PWM techniques, so that by my little efforts they also get benefited. And I'm pleased to inform all of you that I have been getting continuous feedback from some international and mostly national students. There are some students apart from my class, MTech Power Electronics and Electrical Drives class, my own students. I have got a lot of feedback from national students and from some international students who were studying this subject, who were following my video lectures, and they were putting some doubts on YouTube, or they were messaging me, and I was trying to reply to their queries. I was trying to clarify their doubts. Okay, so that gives me a lot of joy. It's a small effort, and I am pleased that some students other than my class students, there were many students throughout the country and some international students who interacted with me, who were watching closely my lectures and who are right now also watching my lectures and giving that feedback. So it's a small effort towards imparting technical education to the students of power electronics and electrical drives. And I again tell you, my dear students, it would not have been possible to cover this syllabus, to cover this course without your cooperation, without your active participation. And I have covered this course in about 66 lectures, 66 hours. It took me 66 hours to cover this course. And in our offline classes in the institute, our class is 1 hour duration. So that way I have delivered 66 lectures, each of 1 hour duration. So if you divide it into 1 hour duration, I have delivered about 66 lectures, video lectures. Okay, so it would not have been possible to deliver as many as 66 lectures if we would have been going through offline classes, because in offline classes we had only 3 to 4 lectures per week, and each lecture was a duration of 1 hour. It was not possible to extend it beyond 1 hour because other teachers also had classes with you. But the advantage of recording video lectures is that you can extend. You have all the time in the world, you can extend. So some of my lectures were of the duration 1.5 hours, some 1 hour and 45 minutes. There were a couple of lectures which were 2 hours or more than 2 hours. So that made total 66 lectures. So with this, I end my today's lecture. I declare the syllabus completed. I advise all of you to go through all these lectures, and in case of any doubts, you please interact with me. I will be very pleased to clarify your doubts. I wish all the best to all of you for forthcoming exams, and I again advise you that you please learn this subject, and during your semester break, try to design various simulation models and try to implement various PWM techniques for power electronic converter systems. All the best to all of you. Thank you very much.